Hey everyone, I'm Josh Adams with Epic. I'm the platform team lead. I'm going to talk about a lot of mobile stuff and some web stuff. So a little intro, the Unreal Engine, you probably know what it is by now at this point, I hope, with everything that's been going on. But for me, I've been there for 10 years. The platform team does pretty much everything that's not Windows, be it consoles or Mac or Linux or mobile, obviously, in the web. And I started bringing Unreal to Dreamcast way back in the day. And we're moving on up to current stuff. So a little about what I'm going to go over. Why mobile is important to us and to you guys. Some of the challenges we face on mobile. Then go over some of the platforms. And then kind of look into the future. And then some fun demos and videos. So why is mobile important? Well, the Nokia or whatever that graphic is very important, obviously. But mobile is a huge market, obviously. There's a lot of money to be made there. So that's pretty obvious. Mobile power is increasing at a good rate. UE4 makes awesome graphics, and it's a good combination with that increasing power. We can work with any size team, be it one person or 300 people. And UE4 is now free to use. And of course, that's good for everyone. So here's my amazing take on the kind of landscape of the mobile scene. We got games like Flappy Bird. It's a very basic 2D game. One guy made crazy amounts of cash for whatever reason. Crossy Road's getting a little up there. It's 3D, pretty basic 3D. They had like 3 guys. And it made some in the millions, which is pretty cool. Clash of Clans, very different. Probably hundreds of people. I don't really know how many people worked on it. But they're making some bang hand over fist there. And then the high-end kind of things, Infinity Blade, we did in UE3. It's about 15 people, and it did pretty well. So if you're like any of these, and I don't see how you couldn't be, then UE4 is for you. OK, so some of the challenges we see on mobile. A lot of things. I'll go over these. So first up, memory. There's often you don't really know how much memory you're going to have at any given time on the device you're running on. Some recent iOS OS versions, they do start guaranteeing how much memory you have, which is pretty nice. You don't get the whole system, obviously, because the OS has to run there. But if you don't know how much you're going to get, you just have to kind of do some testing and find out what you can do. And I'll go over a little bit how we're kind of, one thing we're doing to alleviate this. And it's obviously not very much memory compared to what you get on desktops with 64-bit and 32 gigs of memory and all that. And these high-res screens that are now on mobile devices, you really want high-res textures. But it does not go well. It's not a good combination there. So one thing to do is texture streaming, which textures are obviously the biggest bulk of your memory usage, most likely. So if you do some streaming, and it's all dynamic, you can toss them in and out. OpenGL ES2, there's some extensions to it on various devices that can help with streaming without needing to hitch, like you might have to do without any of the extensions. So for power-wise, another amazingly scientific charts I have here. So I see it is the functionality of mobile is going up very fast. We're getting to D3D11 stuff on mobile these days. It's approaching desktop at a very quick rate. Power, which is in quotes because CPU and GPU power, it's whatever. It's a bad term overall, I guess. But the overall power level is still going up pretty fast on mobile compared to desktop. But it's not going up as fast as the feature set and the functionality. Some reasons are there, obviously, the battery. You can't just go crazy balls to the wall with the power usage because the battery would drain too fast. And they're pretty small. There's just less stuff you can have there. Memory's expensive at those small sizes, et cetera. So another one is multi-touch and tilt. Touch seems like at first the same as a mouse cursor or a mouse click, but without location before you touch, it is obviously very different. You don't get any hover, you don't have any context of what's going on. And then when you got multi-touch and UI systems, then some widgets, you might want to have multiple widgets capturing the fingers at the same time. Our UI system, Slate, now handles that, but it didn't for a while. So that's something to look out for there. We do have this utility, UDK remote, on the App Store. It's kind of a bad name. UDK is our old free UE3 stuff. We should probably rename it to Unreal Remote or something. But It still works with UE4, so if you're using UE4, go look for this utility. It can send multi-touch and tilt stuff to a desktop machine, so you can iterate your multi-touch faster, just like right there on the desktop. So GL ES2 standard. Before I get to that, this is sort of like our whole low to high end where we are in UE4. Phones and tablets are kind of near the bottom, naturally, and desktops at the top. The web is a little bit of a weird one because it has the GPU can go full speed of the desktop machine, but it doesn't have the same functionality as the desktop machines because it's WebGL, which I'll get into, but that's basically OpenGL ES2. So it's kind of in the middle there. But anyway, this is the side of things where I'm going to focus on. The mobile rendering, it's really our biggest difference from the desktop these days. We do forward rendering instead of deferred rendering, where we have single render target at a time, multiple light passes. It's a standard old school rendering style. It's a better fit for mobile, in general. I say mobile, and obviously there's some newer ones that don't fit the standard mobile device, but you know what I mean. For post-processing, we kind of have to simplify it down because these full screen passes are pretty expensive on most of the mobile GPUs out there. So fewer passes, standard lighting, but we do have in Unreal, our full material system is exposed to mobile now. In UE3, we did very handwritten, like 5 shaders for mobile, and you have to set up your materials completely differently on desktop and mobile. It's a big mess. So we are using our full material editor system. You make your content, all the materials the same on desktop and mobile. There is a bit of a speed hit impact there because we do have, it's just a little more intense, and there's a lot more shaders being created this way. But we felt that we needed to make that trade-off so that artists and everyone could make the content the way that it should be made. And we do have branches in our node system that can, for ES2 feature level, you might have like a one texture lookup or whatever, but for desktop, you'd have some crazy animating craziness. And so you can just do that right in the material editor, so then no matter what you're running on, this same material will look different and just kind of lower quality on mobile. And to combat the problem of multiple shader languages, there's HLSL, there's GLSL, and Metal has its own shading language also on iOS. So what we do is we have a cross compiler that will take the HLSL, output GLSL or Metal in a pretty hard to read format, but it helps us work around the fact that we don't have to write all of our shader code 3 times over and getting out of sync and everything. The shader language is it's a big issue there. So as for ES2 itself, it's a standard in quotes. There's so many different extensions going on. The texture streaming, we have 3 different ways of doing texture streaming in the engine, just based on what extensions you have. ES3.1 improves it a lot because it makes a lot of things now standard that were in ES2 extensions. So that really helps a lot. But then, of course, ES3.1, and well, 3.0 and 3.1, they have their own extensions. So it's just kind of moving the problem down the road a little bit. And ES is one of the older APIs, a lot of CPU overhead. It's not one of the nice modern new APIs like Metal or DX12 or Vulkan. Get to that in a little bit. And most of these ES2 devices are tiled GPUs, which is good for mobile, but bad for the multipass rendering, which I talked about a little bit ago, with all the post-processing and all the stuff we need to do for deferred. A little breakdown of the feature sets we have. Our most basic, kind of targeting iPhone 4 devices, which may or may not really exist much anymore, but this would be like a tappy chicken where there's no lighting. You still get the full material editor, but you don't get a lot of nice, pretty effects. Moving up, we add some static lighting for the iPhone, for the 4S. 5S era, we get floating point color, we get some shadows, we get some dynamic lighting. And then up to desktop, which is the full deferred, amazing, awesome superness that you hopefully saw this morning with the Kite demo. But basically, when you're targeting mobile, you kind of have to pick your min-spec device and target that. It's hard to make content that works well on an iPhone 4 and takes advantage of the deferred shading. Just your lighting setup and everything. It's a hard thing to just use scalability to solve. So yeah, just basically pick your min device, and later devices will look better, but at least you're targeting your content made for the whatever's important to you in your business plan. So scalability. Mobile has to be done a little differently. On desktop games, you would have like an options screen where you can choose, hand tweak the user gets to pick, their texture form or quality, shadow quality, all sorts of draw distances, whatever. Those things don't happen. You don't have those kind of setting screens in mobile games. And you can't always query your device for the same scalability settings you might use to pre-populate your desktop settings. So we have this thing called device profiles in the engine. And there's kind of two levels of how we do this. The engine configuration is per platform. It's kind of targeting on the PS4 has this one feature or whatever, and it's never going to change, and we have to just completely change whatever setup. It's kind of a very basic bunch of settings. But then for device profiles, you can override all those settings for your particular device or device class. With iOS, there's so few devices that we just have one device profile per physical device that exists, and that's good enough. Android, there's way too many, so we have kind of buckets of GPU or of devices, and then you can, if you need to, you can target a particular GPU or whatever, and add settings for that one particular thing to optimize it. But mostly it's kind of broken down into buckets. The nice thing with device profiles for us is that we can take the desktop, run it in with a particular device profile, and then you'll get that scalability emulation on desktop, so you can preview what it's going to look like without needing to run on the device. The engine configuration, we don't have that because it's more targeting the capabilities of the platform. So a little overview here. We start out shared settings for your game across all platforms. Then one platform can override one of the settings. Like instead of using the LAN online system, we use Google Play. Then we get down to device profile, and so we'll have like a basic Android set of settings, scalability settings that are just kind of whatever defaults. And then there can be low, medium, high. They can override those base settings, and they can set whatever it needs to set. And then we can further take, say, the mid device profile and then extend that again for one particular GPU. All right, so some iOS stuff here. That's our Zen demo there. It's been the easy mobile platform for us. I mean, pretty straightforward. There's so few devices, much simpler. The provisioning and signing stuff, if you've ever done it, you know it can be a little more painful than on Android. So in UE4 4.7, we've added this UI into the editor that you can import provisions, you can import your certificates, you can see everything you've installed. It will tell you which ones are good and bad, and the green ones there are the ones that will be used when you go to package your game. So we're trying to ease the most painful process part of the whole iOS development. You're welcome. All right, so for iOS, we support Windows and Mac iOS development. The biggest difference is compiling, because there's no iOS compiler on Windows, at least not legally that I know of. Maybe there's one illegally, I don't know. We don't worry about that. So our solution is to just use SSH and rsync to copy all the source files over to a Mac on your network somewhere, trigger some compile commands, bring the things back that you need, like to executable. And then after that, everything's pretty much the same. Cooking, signing the executable. Once it's been signed once on the Mac, we can re-sign it on Windows. And then we can package it up the IPA and then deploy it to a device. You could actually do the code stuff before 4.8, but it wasn't SSH-based, so it was a lot messier and it's kind of a security hole. But if you really care, you can look on a remote tool on Answer Hub and find out how to set up the manual stuff. So a little bit about the Zen Garden demo and Metal. It was Metal, and it was Metal super fast. It's obviously a new API. It's no CPU very little CPU overhead. It was the whole point of it, to get out of the GL stuff. In the demo, we had about 5,000 draw calls at various times, which with Metal now on iOS, we can think in terms of thousands of draw calls. Before, we were in hundreds. So it's like a whole new just order of magnitude of draw calls, different. It's modern, it's object-oriented. There's a lot of nice features in it. It's pretty well, it's fast, it's well-featured. It's clean API. It's new, modern. That was a hashtag I tried to get going. It didn't really work out. There were 3,500 butterflies in this scene here. But yes, it is very Zen. So some other things about Metal of interest. They can do precompiled shaders. So you can take a shader code, convert it to intermediate language offline. It still has to do the final compile with the render state online, but it takes a lot of the processing is done ahead of time. The compiler is only on the Mac, so right now we only support the shader compiling. If you're on a Mac, if you're cooking on a Mac, it'll do the precompile. Metal will support compiling online, so if you do it in Windows, it's fine. Eventually, we'll probably use SSH to just shell over to a Mac to do shader compiling. If you compile offline, it can theoretically produce better code because it can take longer to optimize the code when it's offline. Very simplified resource management in Metal. You just allocate a texture. You can call functions on the texture. You can upload data to it, and buffers are just memory. They allocate the memory for you, but you can still just treat it however you want it to as a buffer and use it for various things. It's really simple and great. They support ASCC textures, which ASCC is the new hotness of texture formats for compressed textures. Very nice. It's the new standard going forward. So yeah, it's the way to go. Parallel rendering, they have support for it right into the API. UE4 is going towards a parallel rendering system where we take our rendering thread and have multiple threads, each generating a bunch of commands to render. And so we'll be adding Metal support for this pretty soon. Right now, there's not a huge number of cores on mobile, on iOS devices, so parallel rendering hasn't been a huge priority, but obviously, as time goes by, we'll get more cores, and it'll be a lot more important. And then we get some pretty cool verification of render state. You can enable verification. It'll run a lot slower, but it's better to do that only when you want to instead of every time. And it'll tell you when you mess things up a lot. And then there's the S code. You can capture a frame. You can recompile your shaders. You can see all the draw calls. You can profile shaders, make changes to the shader, reprofile it on the device. A lot of that they can do in ES2, but it's kind of better in Metal overall. All right, so now Android, the big one, the not-so-easy platform. So there are thousands of models of Android devices, we all know. There's many axes of things that go into a device that affect us. We try to save you guys from dealing with it, but it's good to know about all this stuff anyway. Obviously, the CPU is important. There are 4 models of CPUs we care about: ARM, 32 and 64, and then x86, 32 and 64. That's generally less important than the GPU because your CPU code either compiles or it doesn't for the most part. One thing that's interesting is that you can take an ARM code and run it on an x86 and it'll sort of emulate that and it does work. But if you need a lot of performance, then of course going native x86 code is going to be better. But the GPU is obviously very important, and it's where most of the differences are. There's 4 families: Adreno, the PowerVR, Tegra, and Mali, and they each have their own texture formats to go with it. So that kind of follows from the GPU that's in there. The extensions can vary greatly. The carrier you wouldn't think it matters, but carrier gets in the way where they are the final arbiter of getting you an updated version of the OS and drivers. They can change anything along the way they want to. So it is just another layer that can sometimes can affect things. The OS version, obviously, there's many OS versions. We go all the way back to API 9, which is 2.3, up to 5.01, and we see driver changes and other things happening over time with different versions that causes problems. So, and then, of course, there's the type of Android, Amazon or basic Android. Who knows who else is making Android versions. The chart on the right is kind of sized roughly by how important it is and how much we have to worry about it. So looking around, I found, well, we've had issues where we get a bug for the S4, and we have to ask which S4 is it, and which I didn't realize at first when we first got into Android. But I found on Wikipedia there are 19 models of the S4. A lot of things are similar between them, but here's just 2 of them, and they are very different on pretty much every level, which is pretty interesting. So when you're doing Android stuff, if you're in Asia, it's going to be very different than if you're here, potentially, for your devices. They're not all the same. So some less obvious things that we've run into that I figured I'd just pass along. Shader compiler, they can vary greatly for the GPU and across the driver maker. We have identical shaders. Sometimes on one device, it'll just fail to compile. On other devices, it will sometimes crash inside the compiler. And we have to figure out how to work around and generate code differently. We ran into a bug recently in 5.01 only where certain shaders would just crash. And a lot of testing has to be done, which I'll get to, obviously. The GPU can't just access all of main memory. Sometimes we see devices that can access like 128 megs of main memory or something for all the GPU data. Maybe not that low, but it can vary widely. So that's something to look out for. Interpolators, some devices still only have 8 interpolators. This is how we pass data from vertex to pixel shader. And there's the GL frag chord, which is one of the built-in variables that may or may not count against that 8, and is apparently not in the standard which way they have to go. So something else to look out for. And finally, we have seen devices that report an extension as supported, and then we go to use it, and it just does not work. Scalability was one of them, and this is a very important extension for us because it's how we use our speculators based on that. Being able to pick from a MIP level of a cube map. So what do we do about this? Well, there's the old standby of just throw some hardware at the problem, which is generally more devices. We try to have a kind of set of base 10 devices that cover the gamut of CPUs and GPUs, and then we focus on those 10 primarily, and then other devices we'll still test them, but not as often. And if there's other devices that not many people have or whatever doesn't work, then we'll still release the engine without fixing that potentially because there's just too many. We can't fix every bug for every device all the time. Never throw out any devices you may have. Have your employees bring in their old devices they don't want anymore, put them in the testing pool, whatever. Keep some on old OS versions because that is obviously going to be affecting things. But there are some services that will help out here, like AppThwack. There's TestDroid. They will have hundreds of devices in a room somewhere that they can run your game on. If there's bugs, they will send you the crash log, the output log, all this stuff. You can find out. It costs money, obviously, but it's the only real way to get such broad coverage. So something that we're working on is a UE4 readiness app. Something we just kind of started working on. But it's a very tiny little application. We want to put it on the Google Play Store. But basically, you run this on your device. It will spit out a whole bunch of crap on the screen telling you things that are important to UE4, whether or not your device supports it or at what level, what you can expect to have happen. I just mocked this up in PowerPoint, so it may not look like this. Probably won't look like this. We haven't done the UI part of it yet, but you can sort of see the sort of things that we can run through it. We can try compiling some of the shaders we know cause problems. We can allocate a bunch of memory until it fails, et cetera. So, all right, the Android extension pack. This is something that Google announced last year sometime at Google I/O. Hopefully will save us all on Android. It is basically, if the device supports it, it will be a set of ES31 extensions that you'll have access to. Like geometry shaders, AACC texture format, a bunch of other things in there. You can look at that URL to see the docs on what it means. We use this for the Ravelry demo, which you may have seen on Android on Integra K1, where AEP and then some additional extensions. There's always extensions. We had the full desktop deferred renderer running on a K1 with tessellation and everything. should point out that it is just adding features to OpenGL. It's not a new API. It's not going to make it run faster. It'll just give you access to cool new features. Some random Android things. Java is the devil, in my opinion. We'd use it as little as possible. It's a pain to go back and forth between them. You have to manually add thunks and things. It's just, yeah, it's pretty gross. So we only use it basically when there's no API in C++ to do it. Games that are 50 megs, there's a limit of 50 megs on the Google Play Store. If you're 50 megs, Google has given us a solution in the form of OBB files where it'll automatically download this extra data to your device, and then you can just use it as like a big zip file or whatever. It's arbitrary what's in there. But Amazon doesn't do this. They want your 200 meg APK as a single file. And so we have in our product settings now in UE4, you can select if you want to put your data into the APK or not. Sometimes iteration can be worse if you do it that way because you have to rebuild your APK just to update some content. If they're split, then you don't need to do some of that work for iteration. And at 4.7, we also have added Mac support for Android. We're still trying to figure out the best IDE situation. Obviously, Xcode for Mac and iOS, and you can use that to edit your Android code. But right now, the way we do it is if you're in the editor, you can launch on Android or package for Android. It'll compile the code at that point. Or you can do a command line to compile the Android code. But yeah, we're looking at Android Studio, which doesn't have native code support yet, so under investigation. So the web, also known as WebGL or JavaScript or Mscripton. What we want for deploying to the web is no plugins. So that basically means JavaScript. And Mozilla has a tool called Mscripton, which will take C++ or other strongly typed languages, and it'll output it to a subset of assembly or JavaScript that's assembly-like. It looks like assembly, sort of, but it is straight up JavaScript. So it'll run in any browser still. But if the browser knows about it, it can run really fast. It can take advantage of the fact that the types are 4-byte types or aligned to 4 bytes in the memory buffer, whatever. If the browser doesn't support it, then the speed of it kind of just depends on how good their JavaScript is in the browser. But pretty much most of the browsers now are aware of it. Because Mozilla works with all the browser makers. One thing it does is it pre-allocates a big chunk of memory at the beginning to run. And this is kind of where our biggest issue is with the HTML5 stuff. More in a bit on that one. But 64-bit browsers are coming. They'll be standard very soon. There's early versions of Firefox and Chrome, and Safari has been 64-bit, I think, for a while now. So 64-bit is the future, and then memory issues tend to go away. You still have physical memory to worry about, but it'll make this a lot easier to have big games in a browser. For rendering, as I said before, it's ES2 level of support in WebGL. And we get more extensions in different browsers. The GPU goes at full speed. Once you kick off a draw call and start the GPU going, it's going at just the GPU as fast as it can go. So the CPU is slower, GPU is full speed, so just do fewer draw calls, make them really pretty, do post-processing, go crazy, because you get full power there. WebGL 2 is coming. It'll be ES3 feature set, and it's being worked on right now. So HTML5, the file access is kind of interesting. This is the cause of the memory issues we have right now. UE4 wants to do all of our file operations. Well, some of our file operations are expected to be synchronous. We do it in a thread on platforms that have threads, which JavaScript does not right now. But on JavaScript, to do file operations, it wants to be async. So to do that, you kind of have to leave your main loop, get all the way back out to JavaScript land. It will make sure it'll kick off and pump the file operations, and then we can come back. But since we're expecting to be synchronous, we can't leave our main loop and come back because it breaks everything. So the solution is this virtual file system, which we, in JavaScript, take all the content for your game, preload it into memory. Then when the game is running, it just does a memcopy out of that memory in C++ land. But of course, it's a big memory hog. So something that Mozilla just announced is Interpreter. hard to say, but it's pretty cool. It will allow the JavaScript, it's basically like a set jump, long jump, is my understanding of how it works. You can jump out back to JavaScript, and you can come back into native, process all the file operations, come back into the C++ code where you left off, which is us waiting for the file operation to finish, which will now be finished, and we can go on. So we don't have support for it yet, but because they just announced it. But this will work around the whole need to pre-allocate this huge chunk of memory for the content. So HTML5, it works in all browsers, but as I said, there's extensions, memory issues. They're not all the same for when it allocates a big memory buffer, how the browser handles it. So there's not really that many browsers and OSs to worry about, so just test it. One thing, Win32 version of Chrome on Windows, it doesn't work too well with large projects. In development, our development builds seem to make it not, it'll give the sad tab. Shipping builds tend to work fine in Chrome, but we recommend Firefox as your development browser. Interpreter, as I said, will get around this because we won't have to allocate so much memory. All right, so I'm going to show something in the web now. Got it. It won't have any sound because the sound hookup is not quite there, but once. All right. So this is our shooter game, one of our sample games, running in a browser. Oh, that's the wrong key. So there's bots running around and killing me, obviously. But yeah, this is in Firefox. 64-bit Firefox, but yeah. So there you can see it in the browser. So this is actually a multiplayer demo that Mozilla set up using this content. They have HTML5 running against PC builds on a PC server, and they're showing that at, hold on. They're showing a demo of this in their booth you can play the multiplayer against PC in 2110. All right, so now looking forward a little bit, where we're going. May not quite get here on mobile anytime soon, but we can hope. It's real time with PC now. We saw that feature graph, right? It's coming. So one of the ways we're getting there on iOS anyway is this is kind of my pet project. There's no real timeline for when it's going to be finished, but working on the full deferred renderer in iOS, just like we had it on the K1 with AEP and their extensions. I've been working on getting it in Metal on an iPad Air 2. It's still a tiled GPU. The K1 is not, so it's kind of a better fit for our deferred renderer. And iOS is not, or it is tiled. So we're kind of looking at how to make high-level changes to our algorithms to work better with a tiled GPU and still do the deferred render. We do render targets, which is like crazy. There's 6 MRTs, multiple render targets. That's why I call it that. And we need the A8, which is in the Air 2, to get the wide enough MRT support. Metal does not have geometry shaders, so some of our lighting effects that we're depending on for that, we don't have workaround for that yet. And so definitely a work in progress, but there is, if you're using UE4 in a non-binary version like GitHub, you can actually try turning it on and playing with it, but I don't really recommend it because it's still in progress, but if you really want to, it's there. So I'm going to show Rivalry on iOS, and I cannot stress enough how much of a work in progress this is, but I figured I would show it, my progress on it. This is the first time I'm showing this stuff in public. So I think anti-aliasing is somehow turned off. I'm not sure why, but there's some rendering artifacts. But this is using a G buffer and the full deferred path, and the ground is little.
You want to play? Okay.
Yep, so that's the robbery demo. And go back. Oh, that is the wrong input. Thank you. All right, and then there's GLNext or Vulkan, which has been sort of soft announced, but we don't really know a lot about it in the world. There's going to be a talk on it tomorrow morning. I think it's still called this, maybe called Vulkan, I don't know. But anyway, if you want to learn more about this, it's the OpenGL's answer to the modern API of low overhead, multi-threading, all that stuff. It's interesting. I mean, it will be harder to use, but it's going to get a lot of power out of, away from all the overhead. It's going to, yeah, it'll be good. So, but I can't already talk much about it yet because it's not really announced. So, all right, so WebVR, this is pretty cool. Mozilla is working on this. Also, it's web-based VR, just like the HTML5 stuff is OS and browser independent. WebVR, the idea is to be device independent. So Mozilla and Google are working together on a standard. As we speak, they're working on it. We'll see, hopefully, a draft of the standard soon, I guess. There's support for it in early builds of Firefox and Chrome. And again, Mozilla is showing it in their booth, so go check it out. All right, some game things. First, I figured I'd show a sample of, if I can get a mouse cursor, deploying, how we do deploying to a device. If you used Unreal in the past, you may notice when you go to launch on a device, it can take a little bit of time to get your content on there. So something we've been working on is doing a lot of iterative deployment when possible. So here I have the editor. OK, they're showing up. And let's say I just want to take a material, plop it on the ground. That looks beautiful. And so then I just click launch. Good time for autosave. And so it's already cooked everything that needs to be done. And then it's copying over to this device. Nope. It's not, because I did not put the other cable in. Text setup is fun. I'll try that again. So copied over just a little bit of data over to it. And now, do we see, is this the right input? Oh, gotta switch cables again. Yay, live demos. All right. There we go, OK. So in Windows, right now we don't have it so it's easily automatically runnable. But there is the amazing red material on the floor. So it should have been smoother if the cables were hooked up right. But anyway, you get the idea. So we're trying to make it as fast and easy as possible to see it on device by reducing all the repetitive things that used to happen. So yeah. And back to my slides. All right, now I'm going to show a couple of games made by some of our users of the engine. Project Hit, it's an Android game by Berenson and Nat Games in Korea. It's very high quality mobile title. They're targeting the Galaxy S3 as a minimum that's releasing this year. There was a UE3 game called Blade that did really well, and it's kind of showed that these high-end games can work in Korea and China, and so now there are a lot of UE4 games being made to target that market. So I have a video of it. So when they were making this, they were seeing that on the S3, the full, like, amazing-looking physically based materials were a little much to do on every surface. So they limit it really to the characters and some hero pieces in the environment. The rest is kind of just standard rough materials. Some little budget information to get to 30 frames per second on Galaxy S3, 150,000 polygons. There's 8 to 12 characters on screen at once. The players have 6, 7, 7, 8 bones. The monsters have a few less. So that's pretty good. So Soul Hunter, another Korean game. It looks really good. This one's a little different. It's by just 2 people. They were new to Unreal. They were new to each other, apparently. They had a $600 budget, and they just wanted to see what they could do with just blueprints, marketplace content, and so they just met once a week in a cafe somewhere, and they made this. Cool. So they have now actually added a 3rd member, apparently, and for some of the back-end stuff and just core services, talking to the back-end, that kind of thing. But the gameplay is still all in blueprints. So yeah. That's it. So any questions or anything, hit me up. Yes.
Do you have any like remote deployment for mobile? For example, like you're running our code on a computer, but you have to input stuff on the phone?
Like something not the remote thing? You mean like deploying it over Wi-Fi or something? I'm not. Well, maybe not exactly what you're looking for, but what we're planning in the future for cooking is you would have your device connected, and while you're changing things in the editor, it will just send over updated assets right to the game.
Okay.
But that's kind of somewhere in the near-ish future, but yeah.
That'll still be helpful. Yeah.
Do you have any improvements in 4.7 or 4.8 to the texture compression build process, especially on iOS? We've noticed a huge problem with how long it takes to do all the PVR compression. We have a fairly large mobile project, and even on a fully spec'd out Mac Pro, it can take 4 or 5 hours to do a build on 4.6 clean.
The easiest thing to do is play with this number here.
It's at 0.
If you're at 0 and it's still taking a while, there's not much we can do.
It's only using 1 core, though. That's the big issue. It doesn't seem to be using the machine.
It should be at least compressing all the MIPS of a texture at the same time. And you have DDC, shared DDC set up so that when one person does it, everyone gets it?
That I don't know offhand.
Okay. So derived data cache you can put on a server, and so that as soon as one person sits with the pain of compressing the textures, it gets uploaded to a server, and then everyone else will have access to that.
Oh yeah, the incremental builds aren't too bad. It's when we do a full clean build. It's just the time is ridiculous, and it's not using all the processing power. So I was just wondering if there was any changes in that coming.
No, there aren't changes to that, but it's all the texture compression time, which goes in the DDC. So I mean that shouldn't happen very often until you actually go messing with the textures, or if you get like an engine update and we change how we compress textures or something. But as long as your shared DDC is set up, then you can alleviate it for most people, just not the first one. So.
Hey, how's it going? That was awesome. Thank you for that. My question's twofold. First, with so much experience supporting so many disparate platforms, how do you, from an engineering perspective, like what have you learned about doing that over time? Like, are you still doing like preprocessor statements, or how does that work technically? And second part of the question is, once you have support that you believe to be reliable, what do you guys do for CI? How do you like integrate with app-thwack, and how do you make sure that you like don't regress and maintain that reliability going forward?
Okay, for the first one, we were trying to go away from pound if PS3 or whatever, and it's more a code cleanliness thing of just doing some platform modules you can query programmatically. Do I support this on this given platform? And then each platform would override these values. Not with virtuals, we do some static tricks to some class call static functions or whatever to not pay the virtual overhead. But it's just you have to design and think about what you can pull out that's the same across every platform. And most of it tends to be the same. I mean, there's very little shared or non-shared code in UE4 overall. And we will try to do things where we have like platform groups. So like Mac and iOS can share a lot of the code. So instead of having just copy-paste code, we'll have the Apple platform functionality, and then iOS can extend the one thing for its path setup or whatever, for that kind of thing. But yeah, it's just designing ahead of time, trying to think about how much you can really share, and just do the minimal amount per platform. The second part, I forget your question now. Oh, yes, yeah. So code CI, we just always checking every time anyone checks in code, we have a build system that is sort of exposed to UE4. There's things called GUPB functions you might see in the C# code that we have if you're using UE4, where we can sort of set up, here's a branch or a game, we want to build this game for these platforms, and then we have a build system, an electric commander, that runs the RUBT, Unreal Build Tool, queries these functions, find out what it should be building, so we can sort of dynamically, as coders, we can turn on things to be built. We don't need to go to the build guy and say, hey, can you start building this game for that platform, whatever. For runtime things, we do a lot of, we have a pretty big QA department. app-thwack is something we played with. We haven't tied ourselves to it. We're still sort of figuring out the best one for that. So, a lot of times it just sucks. You just have to have QA. There are 10 Android devices plugged into this computer, and they just go launch, or write a script to do it. That's another thing we're working on now, is making a lot of automation scripts. And I don't know actually how much is in the engine versus some batch files in their own computer somewhere. But hopefully that answers your question. Is that what? What Albus? Testing. Oh, at our booth? Oh, well, before you guys leave, Project Hit that I showed before, we're actually showing it in our booth, at Epic's booth, so you can go and actually play around on a device. There.
Is it on?
Sorry.
Okay, so I just have a quick question. I've played with this more in Unity than I have with UE4, because I haven't had time yet. But when I export to WebGL, what are you using for the networking?
We have that's something that's very new. There is I believe we put support in on the PC side to do web sockets for game networking. I don't actually, unfortunately, know the more details. I do. If you go to Mozilla, I think we can. When they're showing the demo, there'll be people there who probably be able to answer that.
Sure. All right.
Hi there. I'm wondering what kind of options you have for performance profiling on an iOS device.
Xcode has instruments.
Oh, so you recommend using Apple's?
Yeah. I
Okay.
mean, we have our own stats built in. Like you can stat engine, and it'll show you breakdown some of the high-level engine systems, or stat scene rendering for how many meshes are being drawn or whatever. But for the really low-level profiling, just run through instruments, and it'll give much more detailed exactly where it is.
Okay. Would that be able to parse out problems that occur in blueprint code?
Well, you would see a call stack of blueprint code, but it might be hard to understand what's happening there.
Okay.
There should be some decent blueprint profiling. I mean, you'd probably want to go to the engine for that, for stat blueprints or
Okay.
whatever the exact command is. But yeah, I think probably in the engine for that one.
All right. Thank you.
But you can use instruments to see if blueprints are a problem. And if they are, then you can break it out further.